This is Chapter 8, a review of Chapter 8, Measuring and Controlling Quality. I think I will break it up into 2 or 3 different videos. The first portion will be on measurement, and then we'll cover process capability and statistical process control. Measurement refers to when we collect data to quantify a characteristic of the process, product, service, or of the metric of interest. A measure or an indicator is the numerical values or results that we get when we perform some measurement. So generally the term indicator refers to something that does not directly or exclusively measure performance. For example, in an automobile engine performance, we evaluate it based on several different metrics or different indicators, such as oil pressure, RPM, temperature, things like that. So a measurement or a measure, a good measure, should be SMART, the acronym SMART: simple, measurable, actionable, related to the customer and the business operational requirements of the business, and timely. So it must be easy to understand so that the operators can actually use it and they understand how to do it. In other words, they must have clear definitions of what is an error or what's a defect and what's not an error or defect. It must be cost effective so that we're actually benefiting from doing all the measurements. It should be actionable so that it's used in making better decisions and it helps us in our decision-making process. We don't want to just measure for the heck of compiling data. When we must be able to relate it to the needs of not only the customer but the business and the parameters of the operational requirements and parameters that we deal with, so that it's relevant and that it makes sense for the work that we're doing. And it must be available when the measurements must be available when they're needed by the managers or the operators, so that they can use it and be able to make improvements to the process and make decisions about the process. Now, dashboards are summaries of key performance measures. A dashboard generally is 5 or 6 different key performance indicators for a process, and they're usually turned into graphs and charts so that they can visually alert the workers and the managers when there are performance issues or problems at hand. So examples of a dashboard would be, like I said, for example, an engine performance, RPM, oil pressure, temperature, speed. All of those could be indicators. Or at a university, performance of graduate faculty, for instance, could be measured, or indicators of it could be the number of graduate students, masters, and PhD students that they have, the number of articles that they've published in scholarly publications and journals, grant money that they've brought in, how much grant money they've brought in, any awards and recognitions that they've received, things like that. So a unit of work, in order to do measurements, we need to identify or define what a unit of work is. So a unit of work is the output of a process. The unit or the item that we produce can be named is called the unit of work. And nonconformance is a defect or error that we observe in a unit of work. And when a unit of work has a defect or error in it, we say that it's a non-conforming unit of work or a defective unit of work. For example, in textile industry, a unit of work may be defined as, let's say, 100 yards of fabric. And so a nonconformance could be any type of defect that we find in that unit of work, in those 100 yards of fabric. For example, a nonconformance could be a hole in the fabric, a misprint, a tear in the fabric. Any of those could be considered a nonconformance or a defect. A nonconforming unit of work is fabric that has one or more types of defects in it. So it's important to be able to distinguish between nonconformance, a nonconforming unit of work, and number of nonconformances in a unit of work. Okay. In terms of types of quality measurements that we can make, an attribute measurement, there are essentially two types of measurements. There's attribute measurement, which looks to see if defects are present in a unit of work, or maybe it counts the number of defects in a unit of work. So it could be that the unit is considered yes, no, good, bad, yes, it's defective or it's not defective, or it could be that we count the actual number of defects per unit of work. So both of those are considered attribute type measurement. Quality characteristics that are attributes are not measured, they're counted through visual inspection. An example would be the number of defects in 100 yards of fabric, the example that I just gave. So attributes are generally reported as counts or proportions, not as a calculation that we make. On the other hand, quality characteristics that are variable are measured on a continuous scale. Anything such as length or weight of something, or time, or amount of a substance, all of those, for example, are variable characteristics. By amount of substance, I mean, for instance, I don't know, the amount of vitamin A in a food item. So variable quality characteristics are not counted, but they're measured. So we usually have a yardstick, like a scale or some type of a measurement tool that we have to take the measurement with it. So we use devices and equipment for measuring, and that's where the accuracy and precision of the measurement actually comes into play and becomes very important. So attribute measurements can be expressed in two different ways. Proportion nonconforming is a number of nonconforming units that we find divided by the number of units that have been inspected. And then we have NPU, or nonconformances per unit, which is essentially the number of nonconformances divided by the number of units that we have inspected. So again, be careful that number of nonconforming units is not the same as the number of nonconformances, and you'll see that in a minute in one of the examples. So so generally in service we call an error or something, a bad quality characteristic that it represents an error. We call it a nonconformance, sorry, but in manufacturing we call that a defect. So NPU, or nonconformances per unit, can be referred to as defects per unit, or DPU, in a manufacturing setting. So here is example 8.2 in your book. It says a hotel housekeeping manager inspects random samples of rooms each day to verify that they have been cleaned properly. The manager uses a checklist of 12 quality characteristics. For example, bed is properly made, or shampoo bottles are on the sink, or garbage can has been emptied, and so on. So on a particular day, 35 rooms were inspected, and 3 rooms had nonconformances. 1 room had 1 nonconformance, the second room had 3, and the third room had 2 nonconformances. So what we need to do is compute the proportion of non-conforming units. So we had 3 rooms that were inspected, and so 3 rooms out of the 35, that's 0.086, or approximately 8.6% of the rooms were non-conforming, or they had some issue or some problem with them. Now in the same problem, we want to answer this question, which says compute the number of nonconformances per unit, NPU. So total nonconformances were 6, because in this problem we are told that there was 1 nonconformance in one room, the second room had 3, and the third room had 2. So altogether we have 2 plus 1 plus 3, which is 6 nonconformances, and then there were 35 total rooms, so that's 0.171. So that's NPU for this problem. Now, throughput yield, or TY, tells us the number of units that have no nonconformances. Essentially, the units, it tells us the percentage of the units that are good. So and it's computed using this relationship right here. And so in the hotel room example, where remember NPU was 0.17, if you take e to the power of negative 0.171, you get this answer. And so what essentially we're saying is that 84.3% of the hotel rooms meet the quality standards of the manager, which means that 100 minus that, or approximately 16% of the rooms, are expected to not meet the quality standards of the manager. Now remember, in the previous slide we computed percentage of nonconformities to be 8.6%, so that doesn't jive with our 16% here, but that's because of sampling error, and if we had more rooms inspected, those numbers would be closer together. Row throughput yield, or RTY, tells us the total percentage of good units from a system when there are multiple steps, and each step has its own throughput yield. So here's an example. It says Reboard Electronics Incorporated is a reprocessor of electronic boards used in computers. The quality manager is trying to determine the DPU, or defects per unit, and the throughput yield. The quality manager has requested that 500 boards be inspected, and 48 defects were found. So the question is, what is the DPU and what is the throughput yield? So the DPU is the actual number of defects divided by number of units inspected. So that's 48 divided by 500, which is 0.096. And then throughput yield is TY, which is e to the negative DPU, which is e to the negative 0.096. And that's approximately 90.909, which is 90.9%. So 90.9% of the production is going to be good or non-defective. Now in the same problem, we are told if the production process consists of 4 steps, with step 1 having a throughput yield of 98%, the next one having 99%, step 3 having 96%, and step 4 having 97%. What's the throughput yield for the roll throughput yield, or for the entire process? And that is 0.903. So approximately 90.3% of the output altogether rolled, combined, at the end of the production, 90.3% is good or non-defective units. So another measure is DPMO, or defects per million opportunities, which is the number of defects that we've discovered divided by opportunities for error, and then we multiply that by 1,000,000. In service industry, we call that EPMO, which is errors per million. Okay. So here's an example. Over the last year, 752 drug doses were administered at the Good Health Clinic. Quality is measured by the proper dosage as well as the correct drug. So there are two quality characteristics: proper dosage and correct drug. So in two instances, the incorrect size of pill was given, and in one case, the wrong drug was given. At what sigma level is Good Health's process? So to compute this, we must make a distinction or make a note that there are two quality characteristics that are being observed. So there are two different types of opportunities for defect, essentially. One is whether proper dosage was given, and one was whether correct drug was given. In this case, because there were 752 drug doses given, essentially the number of opportunities to make a defect, or to find a defect, or to make an error, is 752 times 2. Even though 752 doses were administered, there were 2 opportunities for error in each, so the total number of opportunities is twice that. So the number of opportunities to make error is this quantity, and the defect rate then is 3 divided by 752 times 2, sorry, and then we multiply that by 1,000,000, and that becomes, that's 1994.7. So to understand at what sigma level, these are the associated sigma levels and DPMO. So given that in our example 1994 falls about over here, so we're somewhere between about 4.5 or so, between 4 to 4.5 is where we are. Okay. So we do all this measurement, and it's important because we need to keep the cost of quality down. So cost of quality is what we pay to avoid poor quality, or what we pay because we produced bad quality, and it's in the hands of the customers. Knowing the cost of quality helps to identify what improvements we should make and where we should make those improvements. We can also use it to see if quality improvement programs are successful. So upper management usually understands money, and quantifying cost of quality is that language that they can relate to and they understand. So that's a very important thing in successful quality management programs, is to make sure that you quantify the cost of quality. So the classifications are prevention, appraisal, internal failure, and external costs of quality. So prevention cost is what we do to avoid making poor quality products before it even leaves the company, before it reaches the hands of the customer. Things like testing, prototyping, training, all of those would qualify as prevention costs. Then we have appraisal costs, and they ensure conformance to requirements. So generally measurement costs, data analysis, any kind of data analysis that we do to detect defects, all of those are parts of appraisal cost. Internal failure cost is what bad quality costs us before it reaches the hands of the customer. So any scrap or rework that we have to do to get the quality right before we ship it out they're part of the internal failure cost. And then the biggie is the external failure costs. So when bad quality products reach the customer, it's just too late. This is when external failure costs are incurred, and people start returning items, or if it's a really bad situation, you may have to recall an item or product. And so all of those are external failure costs. These external failure costs are not only monetary in nature, but they can be devastating to a company because they affect the company's reputation. So